Okay, we're rolling. The session is being recorded and it'll be presented later after it's been authored onto the recorded presentations page here on my TCC Blackboard. Welcome to the session. It's about 9 o'clock in the morning on Tuesday, December the 1st. And today we're covering modules 11 on design, network design, and modules 12 on troubleshooting. And then on Thursday, we're going to have this is not a lab that you guys have to do. It's not a required lab for you, but I'm going to do a demonstration of password recovery on switches and routers. What happens if you come into a place and no one knows the passwords, or you accidentally forget the password. And I'll also show the TFTP function, which is a means of backing up and restoring both the iOS operating system file as well as the startup configuration of the running configuration file. Okay, we'll get started here in just a second. Click another attendance. Okay, let me do my share sessions, share files. Okay, I've chosen this slide number 14 from this 100-slide presentation. It's an advanced Cisco presentation that Cisco made in a seminar about network design, because this is the one single best graphic I have seen on this thing about core distribution and access, which is going to be a topic of this first chapter today. So let's see if I'm allowed to draw on this. Am I allowed to draw on this? Okay, so access layer switches. These are the switches. In our laboratory, we have our little cheap $500 24-port access layer switches. Access layer switches are intended to connect to end devices like employees' desktop PCs, printers, and things of that nature. And access layer switches typically have twisted pair copper cabling to go to the employees' desktop PCs, and the little short black lines that are present on this graphic. And then they have fiber optic cables that go upstream to the higher level switches that interconnect all the offices and buildings of a floor together. So the characteristics we think of when we think of access layer switches are, hang loose, oops, there we go. When we think about access layer switches, we think about they're where you get your connection to the network. So they would go to a desktop PC, or maybe a server, or maybe a printer, and they're typically fast Ethernet or gigabit Ethernet speeds, connected by a copper cable, twisted pair cable, and then we use fiber optic cable, the higher rate of speed, maybe 1 gig or 10 gig, or these days you can get 25, you can get 40, you can get 100 gigabit connections to your upstream devices. The type of security that we're going to enforce at the access layer is port security with MAC addresses. So for example, if the dean is connected to this port right here, I can cause this switch to memorize his MAC address of his PC. And if someone manages to get into the wiring closet and unplug him and plug in their device because they're a spy from Dallas Community College or something like that, they won't have the same MAC address as the dean's computer, and the port security will partition that port off, and they won't be able to steal our secret marketing information and get a head up on us. So access layer switches are the cheapest switches. $500 switches that we have in the lab, the switches that we actually use in our wiring closets to go to our student lab, they're 48-port switches, and they have power over Ethernet. They're more like $2,000. At the distribution layer switches are the ones that all our access layer switches connect to. And they are typically a $20,000 to $500,000 type of switch, which uses all fiber optic connections, downstream to employee desktop PCs, and all fiber optic connections upstream to the core routers, or the core switches. They're going to be the high-speed switching, central switching for the entire enterprise. If we're doing any type of access control list, you remember the access control list and those crazy wildcard masks? That's done at the distribution layer switches. So if we're imposing an access layer switch in a public school environment where the kids in the up to junior high school level and younger, they're not allowed to get to certain places on the internet. We could put an access layer control list on that. And the administrators and principals, well, they can go anywhere they want to. We can give them an access control list that gives them unlimited access to anywhere they need to go to on the internet. So access layer switches or distribution layer switches are typical of what we call multi-layer switches or layer 3 switches. They're instead of a fixed configuration switch like we have at the access layer where it has a fixed 24 or 48 ports, these are like chassis where you can slide in a card, and you can slide in the card with 48 Ethernet ports on it, or you can slide in the card with a bunch of high-speed fiber optic connections on it, sort of custom build your chassis to fit the needs of your company. At the core of our system, the reason I like this graphic is that all the previous graphics I've ever seen just show like this part. And they don't make it clear that you have lots of things at the access layer. You have employee desktop PCs. There's a bunch of floors of employees. You've got wide area network connections to go to our branch offices. You've got an internet connection to give our employees internet connectivity. You've maybe got a data center where you've got a bunch of high-speed data center switches that are connected to all the servers that are in a data center, like we've got downtown at our Trinity River campus. We have the big data center. So when you go and use the net lab, not the net lab, the packet tracer on the student VDI, that's in our data center. So the core layer switches are the ones that are the really big $1 million devices, very high-powered combination switches and routers. They don't have any access control list on them. That would slow them down. We're going to put our access control list at the network layer, to do network filtering at the distribution layer switches. We're going to put our MAC layer filtering on the access layer switches. The core layer switches, we don't want to put any access control list on there because it would slow them down. Access layer switches slow down devices because they interrupt the fast switching and Cisco Express forwarding features that are in the routing functions of those devices. So these are our fast $1 million devices that connect everything together between all our company locations, all the floors of a building that we're using. So that's why I like this particular graphic. Okay, hang loose and I'll go back to we'll take you back to our regular program. Okay, so here we are, the official Chapter 11, Module 11 network design. And I'm going to skip to, not allow me to click in here and skip. I want to go to, here we go. Here's the official stuff about access, distribution, and core layer. So access layers provide the network access to the users, the end devices. Desktop computers and printers are in what we call endpoints, as opposed to routers and switches and firewalls. They're intermediate layer devices that make the choice about how to route stuff, choose the best path to do stuff. So access layer gives network access to the users through their Ethernet connection. And then they in turn connect to, pencil back on, go to the distribution layer switches. So let's look at the distribution layer switches. So the distribution layer switches are going to do some routing functions. These are our typical, I hate what these marketing guys came up with. They call them layer 3 switches. They call them multi-layer switches. They're actually routers and switches all in one box. So next time you come to the in-person lab, look over at that table over by the window to the where the lab manager's office is, and you see a little, it's only about $20,000. It's a distribution layer switch that has plug-in cards. You can slide in I've got a 32-port Ethernet port on it. It's got another plug that plugs in. That's essentially a router on a printed circuit board. But the marketing guys didn't call it a router. They call it a supervisor module. So at the distribution layer, we're going to do some routing. We're going to do quality of service, which is our feature that promotes stuff that is sensitive to latency, like a voice over IP telephone call or the marketing manager's video teleconference that they have every week. That has to be promoted to the head of the line. Otherwise, the latency would kill it, and the marketing managers won't put up with that. They'll complain to the CEO. We'll have to fix our quality of service. And we're going to do security, like with access control lists. So these are typically found in a big wiring closet. And they're going to limit our layer 2 broadcast domains, because how far are broadcasts allowed to propagate into a network? When you issue an ARP request, a broadcast, or a DHCP request, a broadcast from your desktop PC, how far does it penetrate into your network wiring? Well, it goes into your access layer switch, and access layer switches, being switches, are compelled to flood all broadcast, all the other wires, all the other twisted pair cables and fiber optic cables. So when we get up to the distribution layer, that's going to be where we stop our broadcasts. The switch function and the distribution layer chassis switch will go ahead and flood stuff, but when it hits that broadcast, hits that router function, routers don't forward broadcasts. So distribution layer switches connect upwards to access layer switches and downwards to the core layer switches that give us our fast, high-speed connectivity of the entire network. So again, these are about 500 to, this is kind of hard to draw, $2,000 switches. The distribution layer switches are going to be $20,000 to maybe $500,000, and the core layer switches are going to be our super expensive $1 million and over $1 million combination routers and switches that connect everything together. It's the backbone of our network, connects all the different layers together, connects the data center to the WAN connection, to the remote offices, to the internet connection, to all the different floors of the building or buildings on a campus environment like we have. We don't want to have any kind of access control list at the core layer, because it would slow them down. Access control list should only be used when you need the security, and not on a $1 million switch. It's like in Ferris Bueller's Day Off, they have the Maserati and they drive it at 10 miles an hour. Well, they should be driven at 200 miles an hour. What are we going to cripple it for? So high-speed backbone connectivity. And fault isolation refers to the fact that we have multiple connections between the various devices, and we can easily, if one fiber optic cable gets dug up by a number one enemy of fiber optic cables, backhoes, we can restore that and connect it back. If you're a really large organization, the college is a fairly large organization. We have 100,000 students, we have 4,000 or 5,000 employees, we have several locations. So we use a 3-tier type system where we have a core layer, we have a distribution layer, we have an access layer. If you're in a smaller organization, you might not want to use all 3-tier layers. We could sort of collapse the distribution and core layer into one piece. So for example, when I was downtown at the college publishing thing, we had several floors of a building. There would be access layer switches at each one of these individual floors, and then they would collapse down to a combination distribution and core layer that gave us connectivity between the floors, and then connected to a router that went back to our home office. In our case, our router went back to our home headquarters office in Orlando, and Orlando had the internet connection. So this is called a collapsed core network design. So to tell you a story, when I first went to this publishing company in the early 90s, it was a bunch of hubs. There was no sort of hierarchy to it. We had 2 or 3 hubs on each floor. We had 5 floors. We had about 8,000 square feet in the building downtown Fort Worth, near the courthouse. And it was a bunch of hubs that were connected together, and we had collisions, because hubs have collisions. We had broadcasts everywhere. So that was a flat network, and it should have been changed to a hierarchical network. So switch LANs allow us, instead of using hubs, and use Ethernet switches instead of Ethernet hubs. We get rid of all the collisions. We increase the bandwidth. And since switches are smart, hubs are dumb. Don't be a member of the hub club. Be a member of the switch club or the router club. Have layer 2 or layer 3 sophistication. So switch LANs allow us to have quality of service, have security based on the data link layer, Ethernet addresses. We can do traffic management, and they're much more flexible. Okay, so what does scalability mean? I want to be able to grow a network without having to replace the whole thing. I want to have reliability. Let me give you an example of something that is not scalable. In the old days at the camp, I started working here at the campus in like 1981, and we had an old PBX telephone system, which had, they're called line cards. Each line card would support up to 4 telephone sets. And when we ran out of line cards in that, we were growing at the time. Well, let's see, that was so long ago, tuition was $4 an hour. So when we ran out of slots to plug in additional line cards for our telephones, because we were adding courses and adding employees and adding students, we had to come in with a forklift, it's called a forklift upgrade, and tear out that old chassis and put in a brand new chassis that had more cards. That is not scalable. I should have been able to add a new chassis with extra line slots in it without tearing the whole thing out and putting it back in. So scalability, we're going to accomplish this by doing things like redundancy, multiple links, scalable routing protocols, wireless connectivity. So let's look at some of those aspects here. Here we have a wiring diagram where, let's say switch 1 is the wiring closet that connects all our PCs that are in the student lab at the South Campus. And we're going to have a connection both to the distribution layer switch that's upstairs from it in another building, as well as another distribution layer switch that's maybe in the library instead of in the academic building. So if something gets dug up, if a fiber optic cable digs up something, we still have another connection. We don't lose our connections. So we're going to, the definition of fault tolerance. Fault tolerance means if one single component or thing fails, you still can do your IT operations. So you A+ guys, you think of a RAID drive array. I've got 5 drives in a RAID 5 array, and one of the drives fails. Okay, well, we don't know which one's going to fail. Drives fail sometimes. To expect drives to operate forever and never fail is irrational. So we do things like use RAID arrays so that if any one drive fails, little pieces of the data that were stored on that one drive are stored on all the other drives, and we can recover that data. So in a RAID 5 array, we lose a slight percentage of the total capacity. If we take 5, 10 gig, well, how about 10 terabytes? 5, 10 terabyte drives, which would normally add up to 50, well, we get 40. But it's protected. Any one drive can fail, and we shouldn't lose any of our data during the day, even if one of the drives stops working. So with network wiring, what we do is we run additional fiber optic cables to all our upstream devices, and if one device fails, we still have a backup. And we still have the ether channel or link aggregation so that when they are still working, if the backhoes have gone home for the day, well, they did a water project here, they had backhoes on campus several years ago, and they dug up some fiber optic lines. They always do. So when they're all working, we can just aggregate them together. Instead of getting 10 gig over one piece of fiber optic cable, we'll get 20 gig over 2 fiber optic cables. The problem is that normally if we didn't have ether channel or link aggregation, the spanning tree protocol would turn off one of them. So we can use ether channel in Cisco devices or link aggregation generically with other devices to get the bandwidth. And if one fails, we don't have a problem. We still have some bandwidth. So we have something called a failure domain. So in a RAID driver array, the failure domain is the 5 drives. Any one of these drives can fail, and we still have all our data. Now, if the second drive fails, we start losing data. So all these server drives have a feature in them that when one of the drives in the RAID array fails, the light starts blinking red, and the system administrator of the server administrators are notified, and they can put a new drive in there. And these are typically set up so you can plug in a drive without having to power down the whole server, and it'll rebuild the drive in the background until it's fixed. So on a network, when we have a failure domain, this means that we want to have a way of keeping operations going even if something fails. So if we look at your desktop PC, you only have one cable connecting the desktop PC in the lab to the workgroup switches in the hallway. If that cable fails, we don't have a second cable. We don't run duplicate wires to workstations. Well, that's all right. You just slide your chair over to the next workstation and you'll use it and log into this. So routers function as a gateway for a limited number of access layer users, the default gateway, what I call the friendly neighborhood router, to these more inexpensive access layer switches. So our distribution and the core layer switches are our more expensive multi-layer switches, and we typically deploy those in pairs with that X looking connection between them, so that if any one connection fails or any one switch fails, the network continues to operate. We have degraded performance, but we can still operate and still get our work done. And it takes, what, a half a second longer, so we still can generate revenue for the business. So link aggregation is this feature that if I do run, if we're here we are in the South Campus Computer Science Lab, and we have one set of fiber optic cables going over to the library, and we have one set of cables going next door to the academic classroom cluster. And if any one cable gets dug up, we have another connection. If any one of these switches fails because the power supply dies, actually they have duplicate power supplies in these $1 million devices, so if one power supply fails, they keep operating. But let's say someone dug up the power cable to the whole academic classroom building, and all the whole academic classroom building complex went dark. Well, duplicate power supplies won't help there, so instead we would simply reroute over to the library, and the library still has lights, and we'd be able to reach that. So in Ether channel, we can take up to 8 ports, 2 to 8 ports, and combine them together. We call it a port channel. And if we use, say 8 gigabit connections, we get the 8 gigabit through bandwidth of this. So I can take 8 channels and configure them to be a port channel, and then I'll just configure the port channel itself to be a trucking port instead of so that everything is configured properly. Ether channel, he says load balance. It's a kind of a flaky load balance, because once you start like a TCP connection, it'll stay on one wire. There's some guys on the Reddit networking forum that have some means of configuring Cisco routers so that they more or less try to spread the load out in a more even way than if you just take the defaults. Now, Wi-Fi, the college has probably 10 years ago, we embarked on a program to really get Wi-Fi access everywhere on every campus. So if you don't have Wi-Fi access at home, well, you can drive to our college campuses and go to one of the designated parking lots, and you can get our free Wi-Fi access there. So since a lot of people are using laptops or tablets or using the internet browsing feature on their telephones, this gives everybody connectivity. Oh, by the way, they told us that us employees, us faculties, we're not getting desktop PCs anymore. So the desktop in my office is about 4 years old. They're supposed to be replaced every 4 years. So we're getting laptops now and a big super wide screen to go on our desktop when we're in the office, and then we can carry the laptop around when we want to work remotely, work from home. So wireless LANs, Wi-Fi, WLAN, this means anybody can come in and connect. So since you can bring in your virus-ridden, compromised, ransomware laptop into a TCC Campus Connect, we have to use extra special, heavy-duty, ironclad security on our Wi-Fi points to make sure you don't affect our network, as opposed to our computers, which we own and we have control over, and they're plugged into our internet wired system. So that's one of the reasons that you're not allowed to bring in a desktop computer and plug it into our existing network. It doesn't have our endpoint protection software on it that we get from Cisco on all those machines. So routing protocols are a method of sharing the routing table information between networks back and forth. Cisco routers automatically will place all their directly connected networks into the routing table, but in order to get the remote networks and to know how to find them, we either have to use static routing, which is a big drag, or some sort of dynamic routing protocol. So the old routing protocol like RIP and IGRP, the newer Cisco proprietary EIGRP, which is a pretty good routing protocol. We used to use it. TCC used to use EIGRP, but we switched to OSPF about 10 years ago. So OSPF is open standard. It works with everybody's stuff. It's called a link state routing protocol because all of the areas, kind of like a GPS, they build up a exact information of where is the roadmap, what is the way to get from any point to another point in that network. And then we simply summarize that information as we go between one area and another area. So in OSPF, if you recall, always has to have an area 0, the core area, the backbone area. This is the central point for the network. So maybe area 0 would be the Trinity River campus, Area 1 would be the South Campus. Area 51 would be the Southeast Campus. And then when a change occurs in the network, the areas independently resolve that, and we don't have to bother the entire network. So it makes the network more stable. Okay, let's look at some of these. These are the switches that are typical that are found in our, this is not the little cheap $500 switches that we use, the 2960 switches. These are the more expensive switches. These are access layer switches. These are typically the type of switches that will be found in our wiring closets around the corner that I'm not even allowed to go into. The electricians can go in there and mess it up all they want to, but we don't allow Cisco people to go in there. So our LAN team, our IT team manages all those switches. So they typically have, if you look at the switch here, it only has about 24 connections and all that wasted space here. We have very small areas. Typically in corporations, companies, we have very small area that we have specified for our wiring closet. So they're going to use something that's got 48 ports. So in the same space, they can get twice the number of connections. And these connections over to the right, these are high-speed fiber optic connections that will go to the other switches and go through our tunnel system to connect all the buildings together that are in the campus. And these are going to have features like gigabit Ethernet connectivity. Our switches are only fast Ethernet. They're going to have power over Ethernet, so they can power our Wi-Fi access points and our voice over IP telephone systems. In a commercial environment, they would also typically power IP surveillance cameras. We don't have any of those on campus because of student privacy. Cisco bought Meraki, which was another switch manufacturer. And these are the type of switches that you would use in a smaller corporation where you don't want to pay for real managed switches like Cisco switches are. And they have a feature, I'm going to call it, they call it a feature. I think it's a disadvantage where you subscribe to a Meraki web service and you log into a web browser and it configures a switch for you. The only problem is if you stop paying your service maintenance fee for the web subscription, all your switches drop dead. So that's not very good. I prefer Cisco switches because once you configure them, they'll keep working forever. Cisco Switchzilla. I'm going to call Cisco Switchzilla like I call Intel Chipzilla. So Cisco Nexus is their latest platform of switches, from small application access layer switches all the way to these big monsters we see that are the size of a deep freeze. These are over $1 million, so they have lots of plug-in ports. So switches, some switches are sold to service providers or things like internet service providers or data center providers. So they can provide all the things they need to have. So they want to do virtualized machines so they can run a bunch of, I have this Cisco24.com website that you can go and see the slides and some stuff I put on there, useful links for students. And it's like $7 a month. I don't get a whole server for that. I'm sharing that with a bunch of other people that have pictures of their grandchildren and stuff like that. Very low volume sites. So if you need a whole server because you have a high volume site, that's more like $200 or $300 a month. So they're connected to these service manager switches, service provider switches back at a data center somewhere. Now let's talk about form factors. The switches that we have, well, here's the ones that are similar to the ones we have. It's got 48 ports instead of 24 ports. They're fixed configuration. They can't be changed. Here's some fixed configuration switches here. When you buy them, they come with 24 ports or 48 ports. There's not much you can do about it. About the only thing that we can do with our switches that we have in the student Cisco lab is we can plug in a fiber optic transceiver if we want to run fiber optic instead of a twisted pair Ethernet cables from one device to another device. So you're stuck with the features, the configuration, the hardware configuration that came with the switch. I can't add more ports. I can't add an extra power supply. The more expensive modular switches have card slots, and you can plug them in. You can buy a mid-sized chassis or a large chassis and plug in 2,000 ports if you need that in the switching center for a whole data center or for a whole company. So I can add 2 supervisor modules and have the equivalent of 2 routers where if one fails, the other backs it up. I can plug in thousands of fiber optic ports and Ethernet ports onto these devices. But they're very expensive. They're like in the $1 million class. So in the middle are stackable switches. These switches look very similar to the switches we have in the student lab, but in the back, they've got some special plugs that sort of jumper them together, and you can take up to 9 Cisco stackable switches and make the equivalent of what would be a distribution layer switch, a chassis type of a switch at smaller cost. This may be okay for connecting to access layer devices like employee PCs. I don't think I would want to consider these for a data center environment or any kind of distribution or core layer stuff. So he talks about that a rack mount unit, a 1U rack mount unit, is 1 3/4 inches. So you could mash, if you had 10 1IU devices and you put them in a rack, it would take up 17.5 inches of space. So there's a whole kind of a art and science to stuffing these things in racks and making sure there's enough power to handle them and getting them connected to the rest of the devices in the data center or in your enterprise. This port density, our little $500 switches don't have great port density. They've got 24 ports and that's about it. Whereas the switches we have in our wiring closet, they have 48 ports in the space that we have 24. So we have limited distance in our wiring closets. So we get our 48 port switches and they have gigabit connections to the twisted pair Ethernet ports. They've got 10 gigabit fiber optic connections to uplink to all the other switches. They've got power over Ethernet, so they're more like $2,000 instead of $500. And then if we had a multi-story office building, gosh, we might get a big modular layer switch that has a couple hundred ports on it or 1,000 ports on it that we could connect to all these different floors of the building and get our employees connected together. The forwarding rate of a switch is how much it can process, how much data can it process. So non-enterprise switches may not be able to, let's say if I went to the office supply store and bought a 8-port gigabit Ethernet switch, and then I plugged 8 desktop PCs into it, and I ran a program that would generate high volumes of traffic. There's a Linux program called iPerf that'll generate endless traffic so you can speed test your devices. So I'm going to set each of these 8 desktop machines to send a gigabit of data into the switch and see if it can process all that data at the same time. The little $50 8-port gigabit Ethernet switch from Office Depot is not going to be able to do this. It's going to slow down. It's blocking. It's not able to send data continuously. But enterprise quality switches like our Cisco switches, if we plug something into all 24 ports and sent full speed, full tilt data into them, they can handle it. They won't block the data. Particularly in a data center, this is important because servers are always, a bunch of 100 people are connected to a server. They need to be able to have the fastest possible rates. So the wire speed is the data rate. In our switches, we have 24 fast Ethernet 100 megabit ports. And we have the 2 gigabit ports, port G00, G001, or we could plug in a adapter to them and use the fiber optic cable instead of the RJ45. Can't use both at the same time. Now, access layer switches typically don't have to be full wire speed, because what are the chances of everybody downloading something at very high speed at the same time? Well, maybe if Microsoft Windows 10 has a new service pack update being downloaded, they might need to operate at pretty full speed, but users normally don't generate that much traffic. Okay, power over Ethernet is this feature that if the switch is equipped with it, and our little switches in the lab are not equipped with this. They do not have power over Ethernet. The power over Ethernet is the ability to send, a few watts of power, about as much as a Christmas tree light takes. These days, power over Ethernet is up to the point where it can actually power an LED lighting fixture, about 90 watts of power. So an IP telephone, a Wi-Fi access point, an IP surveillance camera, they'd need how much power as a battery would give it? Not that much power. And so to avoid having to hire an electrician and run extra wires up in the ceiling, we have to connect the RJ45 from the Wi-Fi access point to the Ethernet switch in the closet anyway. Just go ahead and have it carry both the data and do some small amount of electrical power over that cable as well. So switches that have this power over Ethernet feature are more expensive than non-power over Ethernet switches. Power over Ethernet as a configuration is beyond the scope of CCNA, but we're mentioning it here solely as a concept. Okay, I don't like this term that these marketing guys, they went to their retreat in Hawaii and drank a bunch of rum and came up with this idea of, oh, well, we can't call them bridges anymore. Bridges are slow. We'll call them switches. And now we have some router blades that we'll plug into these switch chassis. So we're going to call it a multi-layer switch or a layer 3 switch. Really, it's just a switch printed circuit board with Ethernet plugs on it in one slot, and a printed circuit board that duplicates the functions of our actual routers that we have on another slot. And then they give it the fancy marketing name of a multi-layer switch to impress non-technical people like purchasing managers. So they can forward IP packets very quickly. The advantage of using a chassis is that instead of connecting the switches and the routers together with twisted pair Ethernet cables or fiber optic cables, they have a very fast, kind of similar to what you find in the printed circuit board of a computer, very fast data planes, where we can transfer the data at much higher speeds. Since it's in a shielded enclosure, it can transmit the data over short cables much more quickly than the standard Ethernet cable could. Now, this term application-specific integrated circuits, you can get a custom chip made, or you can buy off-the-shelf custom chips that will be all the functions in an Ethernet switch, for example. And since with the technological advantages of electronics technology that's taken place since the 90s, we can shrink these chips to very small sizes. In the same sense that the CPU chips, like the Intel Pentium chips, have gotten much smaller and much faster and have more capabilities in them than they did 20 years ago. So this can take some of the load off the CPU, and the application-specific integrated circuit can do some of that work itself. If you have a desktop PC and you've got maybe you're a gamer, and you've got a high-quality $300 or $600 video graphics adapter card in your PC, the CPU functions in your video graphics card is faster than the CPU chip on your computer itself. And that frees up your computer to do stuff and gives you fast video graphics capability and processing. So here's our considerations for selecting the switch. What's the cost going to be? Well, gosh, the $500 for a standard 24-port Ethernet switch, or if we're really, really cheap, they go down to the office supply store and they buy not an enterprise level switch, but a consumer switch or a small business switch. Port density, we have to have enough in our wiring closet and outside in the hallway. We have to use the 48 port switches because we have to cram hundreds of connections that are present in the business building and the upper floor and the lower floor together. We have to have power over Ethernet because we have Wi-Fi access points, and we have Cisco over IP telephones. I've completely replaced that old PBX system that we used many years ago. Enterprise level switches have to have high reliability because we need to be able to use the system at any hour. The port speed many years ago, well, let's say in the 90s, standard Ethernet, 10 megabit Ethernet was okay. We were doing simple file and print sharing. There was no YouTube, there was no streaming audio and video at that time. Then by about the year 1999-2000, it was more of a fast Ethernet to the client type of technology, which is what we had in our computer science lab at about that time. We got rid of our old 10 megabit hubs and replaced it with 100 megabit Ethernet switches from Cisco. These days, it's pretty much gigabit Ethernet to the desktop is required because everyone's doing massive downloads of Windows 10 service pack updates, a lot of streaming audio and video, and in the case of work from home, because of all this pandemic environment that we got here, we have to support lots of streaming audio and streaming video. The frame buffers in the switch are specialized memory chips that when, say, 10 people are logging into the server in the morning, the frame buffers on that one high-speed port that goes to the server will save up the first guy will get connected directly, and then the remaining 9, they'll be put in their frame and their buffer memory and fed to that gigabit port that goes to the server one at a time. And the switch should be able to be scalable. We should be able to just bolt another 1U rack mount device into the switch rack switch right next to it and add more ports if we add new employees or need to add more servers to our data center. Now, while it's the case that network switches, Ethernet switches, use the destination MAC address to forward data to another port on the switch, or if it's a broadcast, they'll flood it. Routers use the network portion of the network prefix of the destination IP address to route packets. They're going to look at their routing table. They're going to find the best path with the most number of bits that match, and whatever the exit interface is assigned to that, G00 or G01, they'll forward it out that interface. If there's more than one path available, we can have fault tolerance, we can have redundancy. All host machines on the network, he's talking about employee or student desktop machines, will specify that default gateway address. That's the IP address of the local router interface for them to connect to other networks that are not in their room. So routers normally do not forward broadcasts. No one is interested, no one in the science building is interested in your ARP request to the printer because you got to print a lab out. That's wasting bandwidth. So the routers that's between us and the science building will filter these broadcasts. If I'm plugged into the Ethernet switch that's in our laboratory classroom, I just need to do ARP requests to find out what's the MAC address of that particular IP address I'm trying to ping for my lab. It shouldn't be sent to all the other buildings. It wastes too much bandwidth. Routers connect geographically separate locations. So routers, a typical branch office router, like the $1,000 branch office routers that we have in our lab, were designed to connect that branch office location through a leased line of some sort back to the home office or back to an internet service provider. And we'll also, typically in a large organization, we will group users by what application they're running or what department they're in. We want to increase security. Oh, let's say the marketing department doesn't want anybody else trying to spy onto their new secret marketing plan, so it can be given away to a competing junior college. Oh, what a fuzzy diagram. So here's a typical branch office router here. Sort of similar to ours. This is the next generation of Cisco routers, the 4000 series routers that replaced the 1941 series that we've been using. So these are typically $1,000, $2,000 for a small branch office router. This is not a big $1 million router that would be back at the service provider or back at the home office to connect everybody together with. So service provider, or maybe the home office, would have a super big router in the $1 million class. So here's our $1 million class type of devices. They are very expensive routers that have lots of, think of them like a supercomputer. Because remember, the architecture of Cisco routers and switches is essentially desktop computer architecture. There's a CPU, there's RAM, there's ROM, there's disk storage. It's usually flash drives instead of hard disk drives. So a super fast, powerful router will have lots of CPUs, lots of RAM memory. They can have lots of buffers in it at the same time. And since we have, if it's an ISP's router, we have thousands of customers trying to look at that routing table that's in that router that's got 750,000 entries in it, which a little $1,000 branch office router, he wouldn't be able to handle that. So here is the example of the system closed and the system open, where we can see all the processing devices that are plugged into it. And this is a scale of this is bigger than a refrigerator. This is a very large device. Industrial routers are a special type of router that are designed to go in a, let's say it's a factory floor environment and there's oil coming from a lathe and it's dirty and noisy and smelly and there's electrical noise everywhere. So they have ruggedized routers that are suitable for these environments where you can plug in, say you got maybe a machine controlled numerical, computer numerical control CNC type device that requires an Ethernet connection right there on the dirty factory floor. You can plug it into one of these industrial devices and they'll be able to handle it without breaking down because there's a bunch of dirt in the atmosphere. So they're more expensive than what a small business device would be because they're designed to be super rugged, super heavy duty. Here's a small branch office router that kind of looks like your home router. So like home routers, it's got the WAN connection, it's got the 4 LAN ports, it's got some built-in security, and it's good for a small, medium-sized business. Very similar to what you might use in a home environment from a service provider, from a cable company or a telephone company. Aggregation services routers are the more expensive type routers. Again, here's the big refrigerator-sized devices that a service provider would use. You wouldn't use these in your small or medium-sized company. You might use these if you work for a super big company, a nationwide or international scale company that has hundreds or thousands of remote locations to connect together. So for example, when I worked for the Harcourt College publishing business in the 90s, we had about a couple of hundred branch offices all throughout the world. So at our data center in Orlando, they would have these big routers to connect everything together. Yeah, our individual locations, like at Fort Worth, I had a little cheap branch office router. And you can just go up the scale here to the newer Series 5500 routers. This is something that a service provider or an ISP would use. Here is an industrial version of that 4-port home router that we saw earlier, designed to be used in a rugged environment with oil or a lot of harsh environmental dust in the air. We want it to be able to survive that without being clogged up and damaging the connection. Okay, hang loose 1 second. I'm going to stop this and start this. And we are transitioning to module 12, which is the network troubleshooting. Okay, so we're going to look at the documentation process. This is a pet peeve of mine. In a lot of companies, there is no documentation. You may be hired as a consultant, and you may find your only documentation is the startup config file. And nobody has any idea of what's connected to what. Cisco Discovery Protocol is your friend. You can trace stuff out. We'll look at the troubleshooting process and troubleshooting tools, and what are some symptoms and causes of network problems, and troubleshoot some connectivity. So many companies don't have any kind of good documentation. The junior college is pretty good about documentation. The next time you come into our real computer lab, take a look at those little 4-port RJ45 port panels you have at your desktop. You'll see each one of those is labeled with a serial number. We know where every wire goes in the whole enterprise. So we have to know where the wires go to if we can troubleshoot wiring connectivity problems. So we want to make up physical and logical network topology diagrams to know what's connected to what. We want to be able to document our network devices, our routers and switches, so we know what the configuration is. And we want to be able to run tests on them so we can have some sort of baseline idea. The theory here is if something goes wrong and you haven't measured things to create a baseline when everything was operating properly, and then something goes wrong and you start measuring things, you have no idea if this is a good measurement or the bad measurement, because you haven't established a baseline as to what is taking place. So network documentation should be kept in a safe location, and we should keep a backup documentation on the location. If we look at our network diagrams for our labs, it typically looks like a logical, oops, drawing went off, here we go, drawing's off. It looks like this. The lab tells you what the IP addresses are, it shows you the connections between the various devices, gives you the network addresses, and you wire them together and you go and perform your lab. Whereas a physical topology is more like a blueprint. It tells you what room number it's in. It's not so much interested in IP addresses as physically getting everything plugged together from one point to another. So a rack and stack technician might use this to get everything plugged up. Here is a documentation of a router device documentation. Well, it's got the model number, it's got the physical location, it's got what version of the iOS it's running, tells what ports are being used and what their IP addresses are. On the switch, we have similar documentation for the switch ports. In this case, we got 2 ports that have been bonded together to form an ether channel. We have an idea which ports are not in use, so if we need to add more capacity later for the new DIN, we have plugs we can plug them into. And then on devices themselves, our servers and our desktop PCs, what version of the Windows operating system are they running? What's their MAC address? What's their assigned IP address? So that gives us some information about that. So if something goes wrong, we can check the devices and see if they're properly configured. Okay, the baseline is when things are running properly, before there's a problem or a fault and everyone's screaming at you to fix. It's the end of the month. Reconciliation reports are due in today and nothing is working. The networking is not working. Oh no, what do we do? Well, if we do a baseline measurement at several different conditions, we can get some idea of, well, how many bits per second is flowing over this fiber optic cable? How busy is this disk drive channel, this RAID channel array that's on the server? And we're going to measure this on, say Monday morning when people come in and start working, where there's a burst of traffic. We're going to measure it on a Wednesday afternoon at lunch when everyone's gone and there's slower traffic. We're going to measure it on the last business day of the month when everyone's running their end-of-month reports, when there's going to be a big peak of activity. So we get some idea of what's normal around here. Well, what normal traffic do we have at different times of the month or different days of the week? So what type of data are we going to start with? So he says the good thing to start off with is interface utilization and CPU utilization. How many bits of data are flowing out the gigabit ports and the serial ports of our devices? How busy is the CPU on that device, like that router or that switch? Step 2, identify devices and ports of interest. So in this case, they've identified the PC1 is the administrator terminal. And the two servers, server 1 and server 2, that people are doing file and print sharing with the company, router interfaces and key ports on switches. And we're going to look at those with show commands on the routers and switches. On the Windows devices, the servers and the desktop machines, we can use the built-in features in Windows like the event manager and the process manager to see what's going on all these devices. So let's say we want to have a period of 7 days at least, and not more than 6 weeks. How about let's just settle on 2 to 4 week baseline. Make sure it includes the last business day of the month. So maybe from mid-month of 1 month to mid-month of another month, and measure everything. Measure the utilization of the CPUs, measure all the bits of data flows through all the different devices. And then do this every year or two because conditions will change. You'll get new contracts, you'll add new employees or build new branch office locations. So you can have an idea what's happening when the network is performing properly. So here's some devices, here's some show commands. Show commands are our friend in troubleshooting. For Cisco devices, show version, well, that'll tell us what version of the iOS is running. Show how long the device has been running since it last crashed or had the power cut to it. Show IP interface brief, my favorite command for telling what's going on in the lab. If you're having problems with the lab and you ask for help, usually that command, show IP interface brief, and show IP route, I can usually tell what's going on. So you forgot to type a command, you forgot to type no shutdown, or you fat fingered an IP address. Show interfaces shows a big detailed whole page full of information, and that's why I can look for things like collisions, interface resets, drop packets, things of that nature that indicate there might be typically a wiring fault, like corroded RJ45 connection or something like that. I once was called into a company that had all their devices working properly, but they had no documentation. They had no idea what switches and routers were connected to each other. They were Cisco devices. Show CDP neighbors is a good tool for this because it shows you, for example, that the gigabit 00 port of this router you're currently plugged into is connected to the fast port, Ethernet port 0/5 of a switch. Now you can telnet into that switch and do a show CDP on it and sort of branch out and create a whole topology, accurate wiring diagram of what's connected to something else. You have to know what's plugged into something else if you're going to fix something when there's a problem. So a bunch of show commands that are here. if you are using Cisco SmartNet, which is their service maintenance agreement that covers software and hardware, and you're the network administrator, engineer for a company, and something's going wrong and you can't figure it out, well, you're paying Cisco to have them help you. So you can call the SmartNet line, they'll assign a system engineer to you. And the first things he's going to ask you to do is go to that router and type the command show tech support. This is a show everything. It's going to scroll about 200 pages of stuff to your router. You're going to go into TerraTerm and capture everything to a text file, and he's going to have you email that as an attachment to him. Then he's going to be able to show, instead of having you on the phone and have you say, oh, type show interfaces, type show IP interface brief, show IP route, all this stuff. This one command, you'll send that big text file to him, and he'll be able to look at that and figure out exactly what's going on with your router and cure your router problem. Maybe it's a misconfiguration, maybe it's a bad wire connected to it. These guys are experienced at troubleshooting these things. Here is the classical Cisco 3-step troubleshooting process. We're going to gather symptoms. We're going to type show commands, or we're going to ask users what they're experiencing. Now, there's a caveat here. Users might feel that they did something wrong and they would be blamed for it, and they will not be forthcoming with you about what's going on. And it may make it hard for you to figure out what's going on. You might have to go down to the PC and look at it yourself. After you've gathered symptoms, you're going to try to isolate the problem. So you've typed a bunch of show commands and you figured out, oh, maybe 2 switches are connected together, and I think that one of them is set to half duplex and one of them is set to full duplex, and it's causing a bunch of late collisions, for example. So once you've isolated the problem and you've formed a theory or hypothesis of what you think the problem might be, you're going to implement corrective action. In my sample case, I'm going to go to one of the switches and say duplex full instead of duplex half. See if that fixes the problem. If the problem is fixed, I document the solution in the company's problem solution database, because 75% of problems, we had a problem solution database at Harcourt, 75% of the calls coming in had already been seen and already been solved. We don't need to reinvent the wheel again. And that way the solution is in the database and we can quickly look that up and not have to research a problem all over again. However, what if you do half duplex, if you do duplex full and it doesn't solve the problem, what do you do? Well, what you do not do is start doing something else and leave that change that you did, because otherwise you're going to break it 10 ways from Sunday. If it doesn't fix the problem, reverse the command that you put in. That did not fix it. Put it back. You might have caused another problem later when you discover what the real problem is. Some of the Cisco process has a 7-step troubleshooting process where we define the problem, gather information, analyze the information, and then eliminate what it possibly could not be. Then we propose our hypothesis or theory as what the problem might be, test it, and always have a rollback. Because if it doesn't fix the problem, roll back to the way it was before. If it works, document the problem. If it doesn't work, take another way, or if it's beyond your scope to solve it, go to a senior engineer, or if you have Cisco Maintenance SmartNet, you can call Cisco and they'll help you solve the problem. So talking to end users, remember that most end users they don't know about IP subnetting and show commands. You need to talk to them at a less technical detail. So try to get them to tell you with open-ended questions, what's not working? What's the problem? What are you trying to do here? Is it affecting you or just you or other people? For example, a user calls and says, I can't log in. And you say, well, will you step over to your neighbor's machine and see if you can log in from there? And if he can log in from his neighbor's machine, that sort of narrows the problem down. There's something wrong with his machine. On the other hand, if he complains he went to his neighbor's machine and he still could not log in, then you say, well, can your neighbor log into his machine? Yeah. Can your neighbor log into your machine? Yeah. Maybe he has got the caps lock key down, which changes the password and he can't log in. Then we're going to try to determine, when did the problem occur? How does it occur? Did you notice any error messages on there? Is the problem a constant problem, a solid problem that occurs all the time? Or is it an intermittent problem? I'll compare this to when you hear the noise in your car, in your engine, you take it to the repairman and you drive the repairman around, the noise is gone. I can't hear any noise. There's nothing wrong with your engine. That's an intermittent problem. On the other hand, if you got a squeak in there and it's there all the time, the auto technician will know that. Oh, you have a wheel bearing out. We need to change your wheel bearing. You can determine what the problem is because it's a solid problem. Determine if anything has changed since the last time it did work. As an example, we would have people call into our tech support center and say, I can't print. I can't print from your test bank product that you guys publish. And you say, well, what has changed? Did it work yesterday? Well, yeah, it worked yesterday. It's not working today. Did you do anything yesterday? Anything else that might have changed it up? This is the point where users think they'll blame for the problem and they'll say no, but what if they installed a new antivirus program on their machine, or a new antivirus update was published to their machine, and it happened to kill our database for our test bank product? So that was something that changed since the last time. So here are some Cisco iOS commands, besides some shell commands that are listed here. We could do pinging. Pinging is our basic test of whether we have network connectivity between two arbitrary points. Ping doesn't tell you if it doesn't work, you don't know where it didn't work. Traceroute is like ping on steroids. It'll test each router along the path, and if it's a failure between router 3 and router 4, you'll be able to figure that out and narrows down the problem. Telnet is a way of connecting to another device. So if I'm doing show CDP neighbor, I can telnet to my neighbor device. Typically, telnet is unencrypted and we can see your password, so it's not that great of a practice. So we should try to use secure shell whenever possible, because that encrypts everything, not just your name and password, but everything else. A word about debug. Sometimes we turn on the debug statement to test something. Debug is kind of dangerous because it puts an additional extra strain onto a router. So a router that's sort of at the edge where it's just barely performing okay and not dropping many packets, when you turn on debug, you kill Cisco Express forwarding, you kill fast switching, and it can cause more problems to occur. So the good practice with debug is to turn it on only in a limited sense as possible to try to discover what the problem is, and then turn it off again as soon as possible. In the middle of the business day, on the last working day of the month, is not a good time to turn on debug. You're going to start dropping a bunch of packets and your users will complain to you. Now let's talk about the OSI and TCP/IP models. We sort of de-emphasize the OSI, dreaded, feared, and hated OSI 7-layer model now. So hubs are physical layer devices, switches are data link layer devices because they understand Ethernet. Routers are network layer devices, and if we're doing an access control list for TCP established, for example, it even goes up to the transport layer. End user systems that actually generate and receive user data always start all the way up at the application layer, part of the process. So here are a couple of methods here of troubleshooting. Bottom-up method. Let's start at the physical layer. Now, it turns out that a lot of the time the problem is a physical layer problem. A wire has become loose from an RJ45 or has become corroded. So you replace the user's Ethernet cable with another Ethernet cable that solves the problem. It was probably a physical layer problem. You probably proved that it was a bad Ethernet cable. So if you think it's a physical type of problem, start at the physical layer and work your way up. If you think it's a software problem, well, software is in the upper layers. Start at the application layer and work your way down. As you gain more expertise, you will get a feel for, you'll see a problem and you'll think, I think this user has a bad subnet mask. And you're going to start at layer 3 at the network layer, and you're going to correct the subnet mask and see if that fixes the problem. This will come with skill and experience as you get more into the gaining more experience in the field. The follow the path method is troubleshoot from source to destination. Substitution method. Well, that was when I substituted a known good working Ethernet cable for a suspected bad cable and see if that fixes it. If that doesn't fix it, maybe I'll put the other one back, because should always undo anything if it doesn't fix it. We can compare things that don't work with things that do work, like your neighbor's machine. Try to log into your neighbor's machine. And as you get more experience, you can do an educated guess, or what I jokingly call a WAG, a wild ass guess. What could the problem be based upon my years of experience? I think this might be the problem. And I could cut my troubleshooting time down. So this figure shows what when a problem is discovered. If it's a software-oriented problem, we should probably top down and work our way down. If we think it's a hardware type of problem, we're going to do the bottom-up method. If I have previous experience and I've gained some knowledge, then I can go divide and conquer method. Oh, I remember this problem. It looks like it's a bad subnet mask to me. If it's a new problem to you, if you have some experience, then you'll go and use bottom up or top down, depending on whether it's hardware or software, to try to solve it. So here are some troubleshooting tools, network management tools like simple network management protocol devices and monitoring stations. Instead of having to run out and look at all these hundreds of different routers and switches, we can get an idea from a network management software on one screen what's going on. So we can try to be proactive instead of reactive. Proactive is when we can see immediately where there's a problem. Reactive is we have no visibility and the users start calling us in 10 minutes, they're all logging off and can't log on again. Vendors have knowledge bases. For example, Microsoft has got a big knowledge base. You can subscribe to this TechNet and they'll send you all the CDs and it costs about $300. But you can go online and get it for free. Just go to the Microsoft knowledge base online and you can see all the problems their techs have seen and you can try to solve it yourself. We talked about baselining before. We're going to use baselining documentation to try to scope out when everything is working properly, we've got some documentation for it. And then when something goes wrong, we can compare the readings with our baseline readings for when things were working properly. Protocol analyzer, there's a shot of our Wireshark. So back in the 90s, we didn't have this software available. We had to use very expensive $25,000, the sniffer. Orlando had this sniffer hardware that could tap into the network and analyze all the packets running of it. And I called Orlando and said, will you send me my sniffer? I want to check Fort Worth. And they said, you're effing kidding, right? I'm not going to send that to you. No way, it's too expensive. But now anybody can take a cheap $200 laptop and put free Wireshark on it and then be able to analyze what's going on in their network. All 7 layers, all the way from the physical layer up to the application layer. This is a great boom for troubleshooting these days. Other types of tools, digital multimeters can measure, for example, measure the resistance of a wire from one end of the cable to the other to determine if the wire is bad. Cable testers are devices that you can plug RJ45 cables in. They'll tell you if the cable's miswired. Or when a contractor comes in and puts the behind the wall wiring in, the structured cable in, you can use this to test and make sure there's no problems with it. This came in handy for me one time. They wired the corner offices with the wrong types of plugs, and only the people in the corner offices could not connect to the network. And of course, who's in the corner offices? The most important guys who complain the most, the higher up levels. I was able to determine they used the wrong type of RJ45 connector, and I made a call to the cable installers to come back and put the correct one in. I was able to check that with a cable tester because it said, 1 should go to 1, 2 should go to 2, 8 should go to 8, and it told me that it was some other type of connection. Turns out they'd use the improper type of connector. When wiring contractors come in and wire up your joint, they should always certify the cable with cable analyzers. Now, these are not little $100 cable testers. These are $3,000 devices that use time domain reflectometry to make sure that all the cables meet the specifications for category 6 or category 7, whatever wiring you pay them to put into. Portable network analyzers can plug into, someone reports a problem in their cube, you plug it into the wall jack and it scopes back and says, yeah, I'm plugged to the VLAN 10, I'm getting the D8 server address. You can wire a wiring problem, and maybe it's just a problem with your desktop PC. And Cisco makes a device, the Cisco Prime device, that can give us information too. It's expensive though. When we talked about Logging. When you look at your router or switch console port and a port goes up or down and it sort of vanishes off the top of the screen later on, we can use syslog and send all these alerts that would be lost normally to an inexpensive desktop machine with a big hard drive in it. And we can save that information in as detailed as we want to. So in this case, the configuration is shown that some desktop machine that has the IP address of 209.165.200.225 has been configured as a syslog server. And we're going to send all these notifications that would normally go to the screen and be lost forever to the hard drive, and we can study that later if there's some problem. Okay, network problems. Performance is lower than baseline. Symptom is performance is lower than baseline. What could a possible problem be? Well, if I haven't done a baseline, it's going to be hard to compare. But this typically would include underpowered server and overloaded server. Switch or router configurations are not optimal. We have congestion on a low capacity link. We need a faster fiber optic cable. Loss of connectivity could be due to a failed or disconnected cable, or it could be a loose or oxidized connection, less ping. Use the ping on a workstation. You can do ping-T and it'll ping over and over again instead of the default 5 times. If a bunch of them start failing, you've got some sort of internet connectivity lost. You need to troubleshoot your wiring. Network connections or bottlenecks, congestion or bottlenecks. If a previously configured route has failed, maybe he's having to use a slower route instead, and this could give you more congestion or bottlenecks. High CPU utilization rates. And he's not talking about on the desktop Windows machine here. He's talking about on the switch or the router. If we've overloaded it and we've added new employees and new subnets, it could get overloaded, and the device will start dropping packets, or it could even shut down or fail. So we can type some show commands like show processes on a Cisco device will show us how busy the CPU has been. If it's over 50, 60%, you need to increase the capacity. You really need to replace that with a higher performance device. Think of, I've got my old desktop PC that was running Windows 7 on it, and I want to install Windows 10 on it, and Windows 10 is just running terribly slow. Well, that old Windows 7 machine from 15 years ago, it doesn't have enough RAM, it's got a slow CPU. You really need to get a new machine with a faster CPU and more RAM memory in it to handle the problem. Power-related problems. Many of these devices have got fans to cool them down. If the fan stops running, it gets a jammed bearing or something, the device will get too hot and it might shut down. Make sure that they're clear and there's not have any dust in them. Hardware faults, maybe a bad driver disk, bad cabling, grounding problems. This can cause errors as packets and frames are being sent. Cabling faults. Look for cables that have been nicked or damaged. Maybe the wrong type of cable, a poorly crimped connector. Well, swap it with a known good working cable and see if that solves the problem. Attenuation is the sort of the level, the voltage level in a twisted pair cable, or the level of the light in a fiber optic cable just sort of guesses out here and gets too small. You made the cable too long. There's a dirty oxidized contact. The cable is loose and you're not getting good connection through it. Now, twisted pair cables particularly, since they use electricity, they're subject to electrical interference from elevator motors, nearby electrical cables, nearby transmission towers can all interfere with these type of things. Fiber optic cables are pretty much immune to these because they don't use electricity. They just use pulses of light. They're much more reliable. An interface error can cause, he talks about clock rate, incorrect clock source. We don't use the serial cables anymore, so we don't have to worry about that. How about the interface not being turned on? I forgot to tap the no shutdown command. That would cause a loss of connectivity. If you're exceeding the design limits of the device, it's going to be overutilized and it's going to fail much more quickly. Okay, if I want to drive 140 miles an hour on the Autobahn, I want a Maserati, not a Volkswagen. CPU overload. If we have high CPU utilization, it's going to start dropping packets. Pings may be, intermittent and don't respond to all of them. We need a more powerful device. If there's no functionality at the network layer or above, a layer 2 data link layer problem that stops frames being sent across the link, others only cause network problems to degrade, it could be at the network layer. If the network is operating below previously baseline levels that you measured, maybe a path has been lost and using a suboptimal path. Use the extended or continuous ping. Now on a workstation, we type ping-t. On a Cisco switcher device, we type the command ping and then press the enter key without specifying the address, and then we'll get the series of prompts where we can do the extended ping and do it 200,000 times or whatever and stress the system. Broadcasts should be limited to a small layer 2 broadcast domain. No more than 200 or 300 people maybe in a broadcast domain. You can do that with VLANs or use more switches. If we're getting too many broadcasts, of course, anytime a broadcast goes into switch, it's compelled to be flooded out all the other ports, and if there's a bunch of those, that reduces the amount of bandwidth available to everybody else. Now, the console messages themselves they'll send error messages to the console when they detect problems. You should use syslog and save these to a syslog server so that if it's lost off the top of the screen before you get there, you'll be able to look at it and try to figure out what's going on. An encapsulation error is, with Ethernet, that's not so much of a big problem. With the old serial ports, it was possible that one port was HDLC, another port was point-to-point protocol. That's not compatible with each other. With layer 2, data link layer addressing is not available. We can address mapping errors. Framing errors can be caused by noisy telephone lines. You guys probably don't remember the bulletin board systems of the 80s and the 90s. We dialed up using telephone lines, and telephone lines are designed for analog voice communication. They're not designed for digital data. When we get a noisy long distance connection and we get all sorts of noise characters in our line, we just hang up and redial, try to get a cleaner line. Spanning tree protocol, a failure or a loop. This spanning tree protocol is supposed to prevent broadcast storms due to a loop. It turns off the port that would create the loop and prevents those from happening. If you keep changing the topology, SDP is going to keep making changes. Our defense against if we want to increase our bandwidth and not have loops, the terminating of loops, reduce our bandwidth, is to use ether channel and add more lines and bond them together as one device. Okay, he defines network failure as the network is completely or nearly non-functional. Everyone's complaining. And of course, everyone's going to complain to the IT department. Your networking is not working, and we need to get it working. We can't do our jobs. And these are the critical areas that everybody can't do their job. So you have to fix this pronto. Suboptimal performance is this a network layer problem? Is this a server that's the hard drive array, RAID array is being degraded? So that could take time to troubleshoot. General network issues. I can change something in the topology of one part of the network and it may affect something on the other areas of the network. For example, I might define an access control list that solves some problem over in the engineering department, and unknowingly, because I remember about standard access lists go as close as possible to the device being protected, whereas extended access control lists go as close as possible to the infringing devices creating the problem. I could fix the security problem in the engineering lab, and then all of a sudden, no, the engineering people can't log into the payroll server anymore. So change in one part may unknowingly have effects on the other part. You got to keep the whole thing in mind. Connectivity issues, equipment and connectivity problems, power cabling, environmental problems, layer 1 problems like cabling. Is the routing table proper? If it's not in the routing table and the router receives a packet and it's not in the routing table, he can't deliver it. He's got to drop it. If it's a routing process, protocol process like OSPF, OSPF forms this neighborship, this neighborhood relationship with its neighboring routers. Show IP OSPF neighbors, see if they're still on the neighbor table. The topology table is what OSPF forms for all the topological information of how a particular area is wired together. Check that to make sure it's proper, and then check it if something goes wrong. Okay, access control lists have to be applied to the correct interface in the correct direction. And the entry should go from specific to general. You should try to organize the list so that the most hit entries are at the top of the list. It reduces processing time. Don't forget about the implicit deny any at the end of every access control list, because if there's not some permit anywhere, all traffic is denied. Wildcard masks should be simple. For example, the most commonly used wildcard mask would be corresponding to the 255.255.285.0 subnet mask. That's 0.0.0.255. It is possible to do really weird things like let all the people with odd IP addresses be permitted and people with even IP addresses be denied, but that's much more subject to an error. Only correct transport layer protocols be specified in an access control entry. So we have all the ports. We're trying to block port 25 for mail and permit port 80 for web access. We have to make sure that's correct. Correct inbound and outbound ports are specified. The established keyword, this is what home routers do by default. You log into a server, you get the TCP sync ACK. It's put in the table on your home router. And then when the correct response comes back from the server you're logging into, the source and destination port numbers match, and he lets it go back. So if I use the established keyword and don't configure it properly, he laughingly calls it unexpected results. I'm getting a failure of some sort. So uncommon protocols, TCP and UDP are our common transport layer protocols. Watch out for misconfigured access control lists. Okay, network address translation, which we use for IP version 4, we shouldn't have to use with IP version 6 because we have so many additional IP addresses. We shouldn't have to do NAT for that. But in BootP and DHCP, NAT requires valid destination and source IP addresses. So we can use the helper feature like we did to convert that broadcast request into a unicast address so it can survive the trip through the router and get back to the home office where the actual DNS server is. DNS servers can have the same problem, and we can use IP4 helper feature for that too. Simple network management protocol, which uses UDP, not TCP. Just quick and dirty, tell me your show interface command stuff. And IP version 4 helper feature can help with that. If we're doing tunneling and encryption, if it's encrypted, NAT can't process it because he doesn't have the encryption keys. So that could create a problem. Overall, though, NAT is very reliable for the most common applications that people use over the internet, like web access, email, BitTorrent traffic for file transfer, and so forth. Okay, application layer protocols. We got these back in the fundamentals of networking course. Secure shell and telnet is a remote terminal session connection. Telnet is totally unencrypted, so it's kind of dangerous if it's in open. Secure shell is safer because it uses a public-private key pair and encrypts all the information. Hypertext transfer protocol for HTML has too many links for transferring web traffic back and forth. FTP for file transfers between host machines where you use a name and a password and you can change directories. TFTP for very simplified file transfers, typically used for updating the operating system in home routers or cable modems and DSL modems, and used in switches and routers for saving and recovering the configuration file and the iOS operating system file. Simple mail transfer protocol is what you use when you transfer an email. Now, if you're using web-based email like Hotmail or Google Mail, they use web traffic to do this. If you're using the traditional email programs like Microsoft Outlook Express, Eudora email, things about that, they use the pure protocol. Simple mail transfer protocol sends mail, POP picks up the mail. Don't confuse. Look at these two. These are a dyslexic pair. Simple Mail Transfer Protocol and Simple Network Management Protocol. One is for mail, the other is for network monitoring activity. They look the same. Okay, so remember what the Mothers Against Dyslexia, that's DAM, said. Don't mix those two up. DNS is our Directory Information Operator of the Internet that you type in netacad.com, and he translates that into the actual IP address that it needs to be used. Network file system is a system used by Unix and Linux machines that's similar to server message block on Microsoft machines, allow you to connect to a shared drive or a shared printer. Okay, troubleshooting IP connectivity. Bottom-up approach steps when there's no end-to-end connectivity. Number one, check physical connectivity. Two, check for duplex mismatches, particularly from switch-to-switch connections. Three, check data link and network layer addressing. Make sure the addressing is proper. Number four, is the default gateway correct? Can I ping it? Five, ensure that devices are determining the correct path. The routers and the switches doing the proper path determination process. Six, is the transport layer functioning properly? Or seven, are there access control lists that are blocking your traffic? And number eight, they put A at the bottom. I've seen on Reddit, they say DNS. It's always DNS. The DNS server has an improper mapping and you're not able to connect. You cannot expect your users to type in a 32-bit IP address in binary or 128-bit IP version 4 address in hex to connect to something. They're going to type in the friendly English names. That's the purpose of DNS. So end-to-end connectivity problems. Well, let's use our friends ping and traceroute to make sure we have connectivity. In this case, PC1 is trying to get connectivity to server 1, and it's got to go through a bunch of switches and routers to get there. So if the connectivity is at between router 2 and router 3, ping will simply fail. Traceroute will tell us, oh, I can get all the way to R2, I just can't get to R3. And it gives us the ability to troubleshoot it down more specifically. Step one in verifying the physical layer, let's use the show interface command. We're going to look for, around here, we're going to look for input errors, output errors, underruns, overruns, interface resets, things of that nature that indicate there's probably some sort of wiring error or that hardware on this interface port of this device has developed a problem and the device needs to be repaired or replaced. Let's check for duplex mismatches. Now, 15 years ago, 20 years ago, this was a big issue. You would connect two switches together, identical make and model Cisco switches, and one switch would just decide, I'm going to be full duplex. Another switch decided, I'm going to be half duplex. And you would get all sorts of errors like late collisions. So we can go to the command prompt, we can fix this. We can, in this case, he went to the switch on the right and said duplex auto or duplex full would fix it too, and forced it to match the other. Because if they don't agree on duplexicity, you're going to get lots of errors. Check addressing. Okay, so I can type the ARC command on a Windows workstation and see the matching between the IP addresses I've talked to recently and what their physical MAC addresses are. Is ARC resolving properly? How about, am I in the right VLAN? Okay, so in this case, the MAC address on Fast Ethernet 01 should be in VLAN 10, not VLAN 1. He's a workstation. He shouldn't be in VLAN 1. That's for the management people to use. So we'll go to interface port 1 and change it to VLAN 10, and that cures the problem. Now he's in the same work group with the other guys, and he can talk to them. Default gateway. Every individual broadcast domain, everybody that's in this particular network, need to talk to this default gateway. One that's in this network, they need to specify this default gateway. If the default gateway is misconfigured, I can ping PC1 can ping the server just fine. He can ping the server S1 and S2 addresses fine. He won't be able to leave the network. So we can verify the default gateway on a PC. We can type route parameter netstat-r or simply type ipconfig. That'll show it to us on a Linux, Unix machine, ifconfig. We can check that. On our routers and switches, we can, on the router, we can type show IP route. Make sure that the router is proper. Now, remember our IP version 6 zero config philosophy was when they came up with this idea back in 1999 to 2000. We started rolling out IP version 6. And there was 3 different ways that they could get their information. They could use the Slack, cut me some Slack, and I'll just talk to my neighboring router. I'll send them a router solicitation. They'll send me back a router answer and tell me what my default gateway network prefix is. And that will give me access to all the rest of the networks. Or we could expense a real server and set up as a DHCP version 6 server, in which case we have 3 different ways. We could use pure Slack, we could use pure DHCP, or we could get some of it from Slack, get some of it from the DHCP server. 3 options in IPv6, there's only 1 option in IP version 4. So let's make sure, let's verify our path to the destination network. When a router receives a packet, he looks at the destination IP address in that packet and says, do I have an entry in my routing table that matches that? Well, what if I have more than one that matches? I'll use the one that has the longest match. If they both match, I'll do load balancing. What if I have no match? If a default route has been established, I'll forward the packet. If no default route has been established, I have to drop the packet. That's how routers operate. The transport layer, access control list and network address translation configurations can cause a problem with this. So I'm going to try to telnet to router R2 and pretend I'm a web browser. Here's a little trick. You can type telnet destination address, and then port 80 is the port for web. And you should get something like this. You get a bad request because you didn't send a proper HTML code, HTTP code, but you prove you can connect it okay without running a web browser. I had a guy show me that one time. He logged into an email server using telnet and sent a mail because he knew the SMTP commands. Okay, on routers, we want to make sure the access control lists are proper. If they're improperly configured or not, bound to a particular network in the right direction, they're going to cause a problem. In this case, the configuration on the left was improper. The configuration on the right has been properly fixed up. Okay, DNS is in our labs, we don't have DNS. So in our Cisco labs, we can substitute using the host name command and put in the command IP host, make up a name that DNS would normally use and the IP address. And then I can ping that server. Instead of typing in the IP address, I can simply ping it by its name as if I had DNS and it will work okay. In Windows, we can use the NS lookup command and test to make sure our DNS service is working properly. Okay, that's it. I'm going to stop there. Okay, so Thursday in the lab, I will demonstrate TFTP, backing up and restoring the operating system and configurations to TFTP servers. And I'll demonstrate password recovery. This is a very important skill you should have as a CCNA technician or engineer, the ability to go in and recover the password without having to destroy the whole configuration and start all over again, because in most places, there's no documentation. The only documentation is in the existing startup configuration file that's on those devices, which if you don't know the password, you can't get to. So we don't want to destroy the configuration. We just want to replace the enabled secret, whatever it was, with something we know so we can get back to it. Okay, let me stop recording.